Hello everyone and welcome back to another video here on the Polaris School of Quantum of the Hidden Quantum Champion series. In today's video we are going to look at a company called Qunnect, and if that's interesting to you then join me for today's video and let's hop into their website right away. So here we are on the website and it says pioneering solutions for quantum networking. We build hardware to transform telecommunications infrastructure into scalable quantum networks. So as you know, this is not only about quantum computing here, we also talk about other quantum technologies, including quantum sensing and quantum communication. And here today we are clearly in the communication part of the story. So it is about creating transforming telecommunications infrastructure. So you already see it's probably going to use existing infrastructure like fiber, or making use of telecommunication fiber to build those scalable quantum networks. And let's learn about that right away. So how does it work? What is it about? The impossible made possible. Qunnect is the difference. And then there's a video here, which we will not watch for now. And here, I guess it explains us the different components. So field deployable. All of our hardware is built to operate at room temperature without sacrificing the quantum performance. These devices are the key to robust and scalable quantum networks. Then it says multi-device compatible. By utilizing the same atomic foundation, we assure high compatibility between devices while maintaining optimal fiber transmission. Then it says infrastructure friendly. The current telecommunication infrastructure is not designed to preserve quantum information. Our auxiliary devices monitor and compensate for the negative effects of the fiber network. And then finally, dynamic network control. Our AI-enabled software suite monitors each and every component of the multi-modular network in real time, ensuring continuous optimal network performance. So Qunnect is opening a new future of computing power, precision, and exponential scale. See how it works. Down here we see the news feed. I'm recording this in the mid of November. You see the news here from October. US Air Force taps Qunnect to advance quantum networking for defense applications, and so on and so forth. Here, Single Quantum and Qunnect partner with CERN QTI on quantum networking experiments at newly inaugurated quantum lab, and so on and so forth. There's more news here. There's a email newsletter down here, and of course the typical links to their social media. Okay, let's quickly check out the menu up here. So we've seen the home part. Now let's try to understand how it actually works. So how are we creating the quantum internet? There's a video which I'm not going to watch, but there's also some explanation here which is hopefully telling us a little bit about it. So it starts with the point that qubits are fragile. Fibers impose exponential transmission loss, making it impossible to connect quantum devices by directly sending qubits over long distances. And I guess by qubits they mean something like single photons, right? Because of the fact that fibers, I guess, is meaning optical fibers, and there's some transmission loss. So when the photon is traveling through the fiber, it either might get absorbed or it might not get reflected by the fiber. So it will not stay within the fiber, but at some point just go outside. And of course, for telecommunication, that's fine. If you're losing like 1% of the signal, or I don't know, if you're losing 1% of your signal, which is millions of photons, at the end you still have enough that you can measure it with your detector. But if you're losing 1% of the signal in case of a photon, that means every like 100 reflections, basically your photon is lost, and you will not be able to align it perfectly to the fiber. So it will always be reflected somehow. And the fiber is also not perfectly straight, right? It's bending. So you're relying on this reflection. And if there's a transmission loss happening, then okay, you're basically losing. And that's why you need to have a very high transmission or very low loss in order to work with that. Now, this is the problem, right? And then it comes the topic unlimited distance with entanglement. quantum entanglement is not limited by distance, since remote qubits can be entangled by daisy chaining many local entangled sources. Now, quickly on that point, what is entanglement? So in the world of quantum physics, there are two major properties that are relevant for also quantum computers, which are superposition and entanglement. Superposition is something that a single quantum object can have. So think about a qubit, which can have two states, up or down, 1 or 0, whatever you want to call it. A superposition is basically when it is in a state that is neither 0 nor 1, or that is not, let's say, up or down. And it can be a superposition, which basically means there's a probability that when you measure it, it either collapses into the one state or into the other state. And controlling the superposition means that, okay, you cannot exactly say when you measure into which state it will fall, but you can statistically make a prediction whether it will fall into one or the other state. Now, this is the superposition part. Then on the entanglement side, entanglement happens when you have multiple quantum particles. So for example, 2. Now, if you have, for example, in the case of photons, 2 photons, and there are actually some natural processes where this is happening, where exactly 2 photons are emitted. For example, when an electron and a positron, so the electron's antiparticle, are hitting, they're basically annihilating, so they are resolving themselves into thin air. But thin air actually not means that they are gone. It means that they are transforming more or less into 2 photons. And there are some reasons why now these 2 photons have to be entangled, related to conservation laws and so on. But basically, if you're looking at the polarization of the photons, there's a relationship as to, if you're measuring one of those photons polarization, what the other photon's polarization has to be. So there is a relation between us two, but it is not per se defined in which direction, for example, the polarization has to be. So think about a polarization. So polarization is in which plane the photon, which is a wave, right, is oscillating. So you could have one that is oscillating like this. So then you would have a vertical oscillation, but you could also have a horizontal oscillation like this. So then you have 2 polarizations, and now if you entangle 2 photons that have, let's say, opposite polarization scheme, that would mean one can be horizontal and the other one can be vertical, and that's exactly the opposite what I'm showing now, or vice versa. And in a state that, for example, is a superposition and an entanglement, it could mean that, like, okay, you are not in a specifically defined polarization plane, so it could be both at a certain probability, but you always know that when you measure one of them, the other one has to be exactly the opposite. And that is a very particular property of quantum mechanics that is very interesting, because suddenly you start to think, okay, but if I measure one of those particles and the other one is in a different position, and that one here is collapsing, then instantly the other one is for sure encoded in the other direction. Does that mean I can transform, for example, information at a speed faster than light, which is not possible by relativity theory, right? And actually you can show that this doesn't have an impact on the transmission of information per se, but indeed it is a very interesting property, and it could, for example, mean that we have one particle here and the other one is sitting on the sun, and when we are measuring the particle here, it actually automatically defines what the particle state on the sun, for example, is. So that's a very interesting property, and that is indeed also the property that is being used in this quantum encryption method. So you're creating these entangled photons, you're measuring them, and you know by some way that, okay, they have to fulfill certain properties. They have to fulfill, for example, polarization property, and that is then being used to encode quantum information. And that also means that nobody can sit in between, because you cannot reproduce the particle in the superposition again. This is like the non-cloning theorem. But that's for another story. If you want to learn more about that, please let me know in the comment down below, and then I will make a separate video explaining more about the details of this. Now, here it says unlimited distance with entanglement. So again, entanglement plays a very big role, but there's actually this problem that, okay, if you have, for example, a limited transmission, that means you cannot transmit over over super big amounts of distance, because at some point your photon will just be lost. And here the statement is quantum entanglement is not limited by distance, since two remote qubits can be entangled by daisy chaining many local entanglement sources. And that's what you see here. So you see multiple of these sources that are being entangled with each other, and by entangling those with each other, you are basically building a chain that entangles also the outer pair. So these two are entangled because this one is entangled with this and this one is entangled with this. That's at least the idea here. Then it says storage is the key. Temporal control of the qubits in the network is at the core of successful quantum transactions. The only device capable of temporarily synchronizing qubits is a quantum memory. So here we are talking about the quantum memory. And then finally, we have the quantum alone is not enough. It is not all about the quantum devices. The telecom network must be ready to accept qubits. We build the enabling hardware to transform telecommunication infrastructure into a quantum-friendly network for entanglement. So take it to the limit. Quantum Internet is all about scalability, modular units without an extreme cooling or vacuum, low loss, and multiplexed. That's the path we are taking to move from a quantum network to the quantum internet. Explore our products, and then I guess that's what we are going to do next. So we are looking at the products quickly. Products overview. Qunnect is the global leader in developing robust, field-friendly quantum hardware. Our modules are designed for scalable networks, distributed quantum computing, and sensing. Here we have those. They are looking again like some inserts that could go into some standard telecommunication rack or supercomputing rack. Here this looks to me a little bit like fiber connectors. So you see pump and coupling. I guess that's like for pumping laser or something like that. And there it's also said pump, so maybe you're connecting this to this with a fiber. Now this is just best guessing. Let's see what the website is telling us. So the QSRC, Q source. The characteristics of the entangled photons define how widespread a quantum network can be used. Our unique quantum sources are designed to interface with vast majority of quantum computing and sensing platforms. Then we see the QMEM, combining the highest level of quantum and hardware performance, a fully room temperature quantum memory requiring no cryogenic or vacuum, providing on-demand storage and retrieval of qubits with high fidelity. Then we have the QAPC. Regardless of the qubit type, large-scale quantum networking is not possible without optimally compensating for the optical fiber's polarization drift. Our automated polarization compensating devices maintain high channel fidelity with low insertion loss, maximizing network uptime. Then we have the QVAL. Automated and customizable QVAL is designed to monitor the quality of distributed entangled photons between remote nodes in real time, providing essential statistics for practical quantum networks. And then finally, we have here the QLSR, so laser, I guess. Scalable quantum networks require locally precise wavelength reference. QLSR provides near infrared and telecom wavelength lasers, simultaneously stabilizing to an atomic reference for a turnkey solution to drive Q source. Q source is then, again, this one here is the single photon source, I guess, which is being used to create these entangled photons. And this is basically the pump laser that is generating the signal that you're actually needing to have these entangled photons, to create these entangled single photons here. Interested in more specs, contact us, and then I guess, you get information from them. Let's also quickly check out the Carnia here. So now we see the full system. Here it says the Gotham rack. And then in there we see the different units that we've seen before. It says Carnia integrates Qunnect's first-in-class quantum networking components with third-party detectors, time taggers, and white rabbit synchronization electronics to create a turnkey solution for establishing the infrastructure to perform entanglement distribution protocols over fiber. The Carnia rack was first deployed to create Qunnect's NYC networks in New York, Gotham Q, where Qunnect showcased record-breaking performance on deployed commercial-grade fiber, published in August 2024. There's the paper linked. Quick look at, I guess, some graphics from the paper here. So sustainable high rates of real fiber. Over real fiber, every quantum networking protocol relies on the ability to distribute and maintain high rates of entanglement across the network. So data, 15 days of sustained high rate continuous transmission and verification of entangled pairs of the Gotham Q network, which is 34 kilometers of deployed fiber with end-to-end loss of 17.4 decibel. So here we see the dates, right? And this is these 15 days that are being mentioned here in 2023 actually to 2024. And here we see the pair rate, I guess keys per second, K per S, I guess it's keys per second. And then we see how it goes down over time. I don't know what K per KS, but pair rate, I guess, could be that. Quick mention on that. So in order to build this quantum network, this network that is using the properties of quantum particles to encrypt, you actually need to have these pairs, so these photon pairs, these key pairs, to encrypt, because in order to really encrypt the message 100%, there's no 100% safe ever, but in order to encrypt the message in such a way that it's basically impossible to break it, you need a key that is at least as long as the message. And that's the idea here. So you're basically sending those photons continuously, you're measuring them, and then you're using this quantum key that you are distributing by this quantum key distribution to basically encrypt your digitally transferred message. Now that means your bandwidth of communication on this encrypted channel is basically limited by the number of keys that you can distribute. And there are different factors like stability of the source itself. So if you have downtime, of course, this will on average reduce the amount. That's why they're also showing here multiple days of working. And then, of course, there's loss over time. So you see here that it, I guess, slightly goes down, but almost not at all. And then it's also about how reliable these keys also work, as in like how well they can be used. There was also mentioned before, if you, for example, have a shift in the polarization, it might not work anymore. So you need to counteract on this. And these things, they are also being taken into account, right? And indeed, this is now an example of a 34 kilometers distance of fiber. So you cannot do that on an infinite length, but I think you are getting into a range where you can do it between different compute centers, and that already makes it interesting. And indeed, there are also across the globe on multiple different spots tests being executed today in these kind of setups where you have different compute facilities, different centers, and you're running between those on an optical fiber such a measurement. And I think in the US, there's one of the very big phone providers testing also different companies' material, different companies' systems against each other, trying to figure out who has the best key generation, who is most reliable, yada, 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 so that you can actually build a network out of this. Then it says here, built for the real world. Deploying fibers are subject to changing environmental conditions that include polarization drift. Without compensation, the impact of fidelity can render a channel useless for quantum networking. That's what I just mentioned before, right? So that's why you need this compensation. And again, here It shows the compensation over 15 days. Doing this compensation, you see here the fidelity, so basically how many of these, more or less how many % of these keys you can actually use, is in this very upper range here. If you wouldn't apply that, you would see that this polarization shift here is basically destroying your signal over time and you're losing most of the keys. This probably, if I would have to guess, I'm not an expert on this optic stuff, but if I would have to guess, that has something to do with temperature changes. So you see here there's a certain seasonality also in the signal, because the fiber is somewhere in the ground, and then when the weather is changing, you have thermal stress that is within the fiber and within the network, and that might have an impact here. But that's just my best guess. Then it says optimized uptime for real networks. That's also something I mentioned before. So network uptime measures the usability of any network. Real-time automated rapid maintenance of the fiber channel is critical to optimize uptime. And you see here that the overall uptime is quite good. So it's up most of the time. It says 99.8%, which of course is not perfect. And I guess especially in the world of telecommunication, you need to have quite high uptimes. The expectations are pretty high, but it already, I guess, goes into a direction where you could start using that for some applications. But again, I'm not an expert on that. And then finally, we see the unprecedented fidelity for real applications. Different applications have different tolerance for optimal fidelity and transmission rate. At one extreme, networking quantum processors require more than 99%, while secure communication protocols can endure far less stringent performance. So if you want to do that between quantum computers, I guess, quantum processors, you have to have a very high entanglement, because you have to have a very high fidelity, because you're connecting quantum information with quantum information. And if an error is happening here on the connection line between those quantum computers, then you can spread the error across the whole system of computers. So everything will be useless at the end. So you have to have this very high values. While again, for the key generation, you can basically use some techniques like duplicated information or whatever to make sure that if something is wrong with the key, you are not losing the full information, right? And there's some more information again if you're clicking here to get the specs. Now let's quickly also check out the about the company part. So pioneers on the edge of quantum possibility. We are a dedicated team of scientists, engineers, and developers pushing quantum technology toward unparalleled scale. Again, there's a video here which we are not going to watch, and then we see the team as well as the directors. So here we have the different chief directors. You see, for example, here Nicole Connor, which is director and partner at Airbus Ventures. The chief technology officer, Mel Flamand, and then Noel Goddard as the chief executive officer, so the CEO, and Mark Tolbert as director, president, and CEO at Toptica USA. And Toptica is again something that might ring a bell to you. Otherwise, check out the Hidden Champions playlist. There might be something for you. And here, that's basically the team of all the talented engineers and quantum people that are working on this. And here it says, our mission critical collective. In this challenging quantum world, we are not alone. Qunnect relies on a strong ecosystem and affiliation with institutions that have paved the way with decades of scientific research. From all of what I've seen, I would guess that they are based in the US. Let's quickly check if we can find something here. So here it says New York. So I guess that's where they are based, a New York-based company. And with that, I would actually like to already close today's session again. If you liked it, please make sure to leave a like at this video. If you don't want to miss out on the next one, make sure to subscribe to the channel. And with that, as always, stay hydrated and see you in the next one. Bye bye.